Welcome to this presentation on the topic of Introduction to Stochastic Processes. We will study briefly stochastic processes, time series. We will see what is meant by stationarity, autocovariance function, and then white noise. A stochastic process is a statistical phenomenon that evolves in time according to probabilistic laws. A realization is a sample of the many possibilities that a process can take, also known as population. A time series is a set of values sampled from the process sequentially. A time series is a particular realization of the process. A discrete time series is a set of observations made at discrete times. A deterministic time series is one whose future values can be generated by a known or a mathematical function, whereas a stochastic time series is one whose future values can be described only by some probabilistic distribution. Now let us consider a discrete time series consisting of u of t1, u of t2 and so on all the way up to u of tn, comprising n observations of a stochastic process. The joint probability distribution function, which is also known as PDF, of u of tk, k going from 1 through n, describes the probability that the random variable u takes on the values u equals small u of tk jointly in a sequence of samples. A stochastic process is said to be strictly stationary if the joint PDF associated with the n observations taken at t1 through tn is identical to the joint PDF associated with another set of n observations taken at times t1 plus k, t2 plus k and so on tn plus k. Here we have collection of t1 through tn. Now we have the same thing but shifted by k, and n and k is arbitrary. That is, for all n and k this property should hold. Then we say that the stochastic process is strictly stationary. A discrete time series is strictly stationary if the joint PDF of a set of observations remains unaffected by shifting all the times of observation forward or backward by an integer k. As a result, stationarity implies that properties of the PDF such as mean, variance and higher order moments do not change with time. This is the most important benefit of the property of stationarity. Alright, the mean does not change with time. So what is the expression? Here we see it. This is defined as mu sub u. In fact, this symbol mu is reserved for mean, is equal to expectation of ut. We use this symbol script e like this to denote expectation, integrated from minus infinity to plus infinity of the process u into p of u, where p is the PDF of ut, into du. I have interchangeably used ut and u. Ut denotes u as a function of time. Here it is written without that explicit mention. So that is the mean. Next is the variance. What is the variance of a stationary process? It is nothing but expectation of u sub t minus the mean. The difference is squared, expectation taken, and that is denoted by sigma sub u whole squared equals this integral, where we once again have u minus mu squared times PDF, p is the PDF, u into du. As I mentioned earlier, I have used u and ut interchangeably here. We will consider the important notion of autocovariance function, which is abbreviated as ACF. What is the use of ACF? It helps understand the interdependence of samples of time series, for example whether they are periodic, independent, etc. In the book I have an example that shows how ACF can be used to identify periodic functions. The ACF of a stochastic time series is defined as gamma of t comma s equals expectation of ut minus mu t times us minus mu s. So this u sub t means it is the value of u taken at time t, this is the value of u taken as s, and you have the mean at that point and then the mean once again at that point, expectation, and we reserve the symbol gamma for ACF in this course, and then it is t comma s. So t is the first time, s is the second time here. It turns out that for a stationary time series the mean is constant, and hence the dependence, this dependence is only a function of the lag L equals t minus s, only the difference between the two time t and s. This simplification results in the following: you no longer have to say mu of t, mu of s here like this. This means mu of u evaluated at s, mu of u evaluated at t. Instead, because mu is constant, we can say it is mu sub u, which is the same at all times, and the difference L is t minus s is used here. You just need the difference between the two, and you have the first index appearing here u sub t, the second index appearing here u sub s, and of course in the place of s we have written t minus L. From here you can see that s is equal to t minus L, and of course remember that if L is a positive index, then the second index is smaller than the first index. That is the way I remember. You may find it useful to make a note of this. And there is another property: ACF of a stationary time series is symmetric about the lag L. L is the difference t minus s, it is known as lag as well. And what is the symmetric property? Gamma uu of L equals gamma uu of minus L. That is because these two commute, you can change the order and you get L or minus L depending on which one you have first. These are some of the properties of the autocovariance function. We will use this extensively in the rest of the lectures in this week. From the previous slide, ACF of the stationary process was defined like this, with mu u being constant used throughout. It takes the largest value at the lag L equals 0, that is when first quantity equals the second quantity. In practice, we use a normalized function known as the autocorrelation function rho uu, which is given by this expression, which is gamma uu of L divided by gamma uu of 0, that is defined as rho uu of L, and as mentioned earlier, this gamma uu of 0 is the largest, so this rho is less than 1. We will briefly look at the notion of white noise next. The discrete time white noise sequence Xi of k is a set of independent, identically distributed values belonging to a stationary stochastic process. Some of the properties are listed now. The mean of white noise is 0. The ACF of a white noise sequence is given by this expression. Remember, we use the symbol gamma and C of k is equal to the variance of this white noise times delta of k. This is the same impulse signal we saw earlier in this course when we were talking about convolution, Z transform and so on. And as a result of this definition, we see that when the index k is equal to 0, it takes the value of sigma c squared, and for all other k values it becomes 0. So that is the ACF of a white noise sequence. What it means is that if k is not equal to 0 here in the index, then the value also is 0. In other words, there is no correlation between the white noise signal taken at time instant k with some other time instant. So long as the two time instances are different, you will get the value 0. And because of this property, we know that the Z transform of delta of k is 1. As a result, the Z transform of ACF of white noise, that is the Z transform of this gamma, is equal to sigma CF squared. Now we can get Fourier transform from the Z transform by substituting Z equals exponential j omega, but then it is a constant here. As a result, we get the Fourier transform also to be a constant. In fact, it is the same value, sigma c squared. White noise by itself has infinite energy because white noise never becomes 0, it always has some non-zero components whatever time interval you choose. So when you take the interval minus infinity to plus infinity and you square it, add it, you see that you will get infinity when you do that. So we say that white noise by itself has infinite energy, so it has no Fourier transform. But on the other hand, Fourier transform of ACF exists, it is finite, it is given by sigma c squared. We will conclude this video with an introduction of cross covariance function, which is abbreviated as CCF. It is a measure of dependence between samples of a time series u of k and samples of another time series y of s. In this course, we will take often u as input to our system and y as the output. For stationary time series, this CCF is only a function of the distance between the samples, that is the lag L. L is the difference between k and s. For example, the CCF of a stationary process is given by this expression. Once again, I write it in terms of t and s. In the case of ACF, you did not have to worry about the order in which this u and y came, t and s came, but here you have to be a little careful. I write the t first, I write the s next. S is of course t minus L, as you can see here, and remember, if L is positive, this second index is a smaller one. That is how I remember. So this is gamma uy. We use gamma once again for this correlation, but then we indicate by u and y that this is a cross correlation function between u and y, and it is a function of only the difference, which is t minus s. It is easy for you to verify that the CCF of two time series satisfy this relation. If you change the order, then you will get a negative sign here. This brings us to the end of this presentation. In this presentation, we have introduced a lot of concepts, many of which may be known to you. Whether you know it or not, you may find it useful to go through this a few times. There is a lot more information available on all of these in the textbook and of course available on the internet as well. If you have any questions, please post them in the discussion forum. We will try to answer them. It is important for you to go through this video a few times to understand what concepts are implied. I would also urge you to go through the examples given in the book. Thank you for joining. Goodbye.